Hi everyone, my name is Ludwig Sidemark and I would like to present our work on Vergence matching, inferring attention to objects in 3D environments for gaze-assisted selection. And this work was made in collaboration with my co-authors Christopher Clark, Joshua Noon, Matthias Lisbeck, Ken Pfeuffer and Hans Gellersen. So we introduced Vergence matching, which is an interaction technique that uses motion correlation and eye vergence to detect small targets in 3D environments. So Vergence eye movements are performed as they focus on a target that moves back and forth relative to the user in the depth plane. And correlating the Vergence movement with the object depth determines the attended target. So Vergence matching is then independent of target size, and we propose it to assist with selection of small objects that are difficult to attain by raycasting from hand, head or eyes due to jitter or imprecise tracking. And this capability allows a novel way of tackling the challenge of interaction with small targets in 3D environments. For the design of Vergence matching, we build on insights from previous work on motion correlation and on Vergence-based interaction. So Smooth Pursuit's eye movements are characterized by the continuous and smooth motion of the eyes and has been exploited for interaction through motion correlation by inducing motion on targets and correlating the target and the eye movement to identify which target the user is following. And this technique enables the selection of very small targets, for example, on a smartwatch, and has proven useful for general and occluded selection in VR. And Vergence eye movements are when the eyes moves in opposite directions and naturally occur when the users shift their visual focus between depth to maintain binocular vision. And several works have investigated Vergence-based interaction in binocular 3D environments to decide whether the user is looking at the world or at an interface, or as X-ray to see occluded objects. And a closely related paper is Ahn et al.'s Vergence, which provides a feasibility assessment of combining Vergence eye movements and motion correlation by overlaying visual stimuli that move horizontally to control objects in the scene. And we build on this work by inducing back and forth movements on objects within the environment and using multiple concurrent motions to allow for a greater variety of applications and techniques. So Vergence matching is defined by the following steps. So first, Vergence matching selects relevant objects to minimize distractions from depth movements, and this reduces the unique trajectories and prioritizes potential objects of interest. And each candidate object is then given a unique motion perpendicular to the user on the depth axis, allowing the system to distinguish the user's focus. And as Vergence movements are one-dimensional, they are defined by the following characteristics. So first, the amplitude of the Vergence eye movement is non-linearly correlated with object distance. And this means that you require larger motion amplitude for distant objects to induce the same Vergence movement. So to account for this and aid matching, object distances are translated into the expected Vergence angle. And to maintain a constant rate of change of a Vergence angle, object speed must then be nonlinear. So we therefore determine speed based on the cycle time. So how far does it go for a movement to go back and forth? And then we also rely on phase to make motions temporarily unique as possible. And the type of depth movement induced on candidate objects is also very important. So whether the movement is linear or harmonic. And this is also something that you need to take into account. And we look into all of these objects in our first study. And then finally, object depth changes may also cause occlusion when it moves back and forth, which may affect user focus. So we modify object size during depth movement to maintain consistent visual size. So to detect user attention, Vergence matching correlates the movement of each candidate object with the user's eye Vergence movement using the Pearson correlation coefficient. And we use pupil positions for gaze input, which does not require calibration, and the target's calculated Vergence angle as target input. And since Vergence is a reactive movement and has inherent lag between object and user movements, this must be considered for accurate correlation. So we conducted a VR user study to collect data on eye movements while following moving targets to validate the effectiveness and robustness of our technique in detecting attention. And we focused on two main research questions. So first, can we robustly detect Vergence eye movements directed at single targets? And two, can we display multiple simultaneous targets without false detection? And we also investigated the impact of cycle time amplitude, target scaling, and other factors related to Vergence matching on attention detection performance. So we conducted 2 tasks to understand Vergence matching better. The first task involves studying slow Vergence eye movement's ability to track moving targets with varying motion parameters. And the second task examined the robustness of Vergence matching to accidental activation during naturalistic gaze behavior. So I will quickly go over the results, and please refer to the paper for full details. So first, our analysis showed that the delay between gaze and target was generally between 160 to 230 milliseconds and needs to be accounted for. We also found that participants could track linear and harmonic motions equally well, but the transition from convergence to divergence and vice versa was more harmonic in nature, leading to higher performance for harmonic motions, as you can see in the picture. We also saw that faster and larger amplitudes resulted in better performance, as you can see in the picture, likely because they led to more distinguishable Vergence movements and higher true positive rates. Shorter cycle times led to more frequent shifts in Vergence direction, which may also be less common in natural environments, resulting in low false positive rates. And our results also show that Vergence matching can distinguish between 2 or 4 simultaneous targets without impacting detection performance significantly. However, adding more targets led to deteriorating performance due to the one-dimensional aspect of Vergence movements. So our study validates that Vergence matching is an effective attention detection technique that is robust to accidental detection caused by natural gaze behavior. We also find that harmonic motions with high amplitude and low cycle time are optimal for correlation, and we suggest limited exploration of concurrent motions to 4 targets. So our results then led to 2 Vergence matching techniques, a threshold-based technique for hands-free selection and a trigger-assistant technique using a controller for more control. So the first technique is a threshold-based variant of the Vergence matching, which for the user works similarly to a typical gaze fixation dwell technique. However, users simply focus on the moving target then until a correlation threshold is reached, which then triggers a selection. We also created a trigger-assistant version of the Vergence matching technique, which gives users more control over selection by using a trigger, such as a button press on a controller. And in this technique, you highlight the candidate target with the highest mean correlation, and the user then confirms selection when the trigger is activated. And this avoids issues with having to reach a specific threshold for selection, and may also reduce the Midas touch problem because the user has full control when a selection happens. So we did a second study to evaluate user performance and perception of Vergence matching by focusing on the ability to select in small targets and to compare these 2 techniques. And we also examined whether having 2 or 4 simultaneous motion had any effect on the techniques. And what we had was that we made participants quickly and accurately select a target from 10 spheres, and these targets had different widths, including one smaller than the typical eye tracking error. And then we also tested how target distance affected selection. The evaluation showed that Vergence matching can select very small targets. So the smallest target width tested was 0.25 degrees, which is equivalent to only 4.4 millimeters at a distance of 1 meter. And although we can select small targets, we found that the completion time is much slower compared to other techniques such as dwell. However, we found similarly high completion times for other motion correlation techniques. We also found that Vergence matching has limitations in terms of error rates in some conditions due to its movements in one dimension. And this trade-off may affect scalability and modality choice, and also led to a preference for fewer simultaneous motions. And then some participants also experienced double vision when selecting small targets at close distances, which may have contributed to these previous results. And this could be due to ocular issues such as convergence insufficiency or limitations of head-mounted displays with fixed focal planes. So, to finish off this talk, Vergence matching extends gaze-based interactions in VR by allowing users to attend to very small targets, addressing a key challenge in inferring attention. And Vergence matching uses slow Vergence movements, which distinguishes it from natural gaze behavior. This makes it effective across different contexts and environments where slow Vergence is rare. And despite its limitations, Vergence matching has unique advantages that makes it compelling as a complement to traditional gaze-based techniques. So that is all from my talk. Thank you very much for listening.